we continue with our example potential V8. It is the most general potential constructed using the complex scalar field phi, transforming under the dihedral group D6. Once we have the potential, we have a set of stationary points. Let phi 0c be one of the stationary points of this potential obtained for a given set of coefficients. And I have marked this stationary point in the figure here. If you change the coefficients a little bit, this stationary point will also change. And this is shown in the figure as the shaded region. As you can see, the shaded region is all around the original stationary point. We can consider the stationary point as a map from the space of the coefficients to the space of the field. As you change the coefficients, the stationary point will also change. This is another example where I start with the stationary point in the real axis. If you change the coefficients, what you will observe is that the resulting stationary points are aligned along the real axis only. They will not be spread around the original point. At this moment, I will not explain why such a thing happens, but it is true. So because of this, we obtain a constraint on the stationary point, which is the imaginary part of the stationary point equal to 0. I call this constraint an intrinsic constraint. Intrinsic because the constraint arises from the properties of the group itself. I will give another example of intrinsic constraint. Suppose we start with a point at an angle 2 pi by 3 and we change the coefficients. What you would see is that the stationary point will move along this line at the angle 2 pi by 3. So here the constraint is imaginary part divided by real part of the stationary point is minus root 3, where minus root 3 is nothing but tan of 2 pi by 3. Why are we concerned about these constraints on the stationary points? So when we have a scalar field and a potential, due to this spontaneous symmetry breaking, the field acquires a vacuum alignment. And this vacuum alignment will be one among these stationary points. And from the vacuum expectation value, we obtain the fermion mass matrices. The properties of the fermion mass matrices can be measured in particle physics experiments. Therefore, the constraints on the stationary points have a direct impact on the measurements that we make in the experiments. Therefore, we need to study and understand these constraints on the stationary points. Now I am showing you a different scenario. We start with a point in the imaginary axis. And if you change the coefficients, what you would see is that you get stationary points all around this blue shaded region. That means we do not have any constraint. However, if we impose the constraints C2 equal to 0, C4 equal to 0, and C8 equal to 0 on the coefficients themselves, and if you alter the other coefficients only, then what you would observe is that the mapped stationary point will vary only along the imaginary axis. In other words, we obtain this constraint that real part of phi 0 c equal to 0. I call this constraint an extrinsic constraint. Extrinsic because this is obtained as a result of constraints imposed on the coefficients in the potential. This is different from the previous case where the constraints on the stationary point naturally arises because of the properties of the group only. Here I have given an extreme example of an extrinsic constraint. So you start with some random point on the plane. And now if you change the coefficients, then you would see that the stationary point will be spread all around it. But it is possible to obtain a constraint of the form imaginary part by real part of phi 0 c is equal to tan alpha, where alpha is the slope of this line. If we impose some complicated constraints on the coefficients. So because of those complicated constraints that you apply on the coefficients, you can obtain the stationary point to move only along this line at an angle alpha. And you obtain this particular extrinsic constraint. There is a small subtlety here. In particle physics, only terms up to fourth order are renormalizable. So higher order terms are suppressed. So in this particular potential, the coefficients of all terms of order higher than 4 should be very small. And as a result, it doesn't make much sense to impose constraints among coefficients of different orders. This can be overcome by introducing certain fields called driving fields. In a more complicated scenario with driving fields, it is quite possible to have a renormalizable theory where I impose constraints on the coefficients and obtain extrinsic constraints of this particular form where we have imaginary part by real part of phi 0 c equal to some angle tan alpha. Now the question is, does it make much sense to obtain such constraints? We started with the dihedral group D6, which is the symmetry group of an equilateral triangle. And in the end, we got this constraint with some arbitrary angle alpha, which has nothing to do with the symmetries of the equilateral triangle. So if you claim that this constraint with alpha is a consequence of the D6 symmetry, it doesn't make any sense. In the Newtonov physics literature, most of the papers utilize extrinsic constraints. Others, which include me also, often impose constraints on the coefficients of the potential to obtain constraints on the stationary points which they wish to have. Many authors do not seem to be aware of the fact that some of the constraints on the stationary points are originating from the properties of the group, while some others are originating from the constraints that you impose on the coefficients. So, in order to clear this up, I have specifically defined them as intrinsic and extrinsic in the current paper. And in many papers, we also see that authors choose vacuum alignments in an ad hoc manner without constructing any potential. But if you carefully examine these alignments, you can show that they cannot be obtained without imposing constraints on the coefficients of the potential. Of course, some authors acknowledge that they have to impose constraints on the coefficients to obtain the results that they want. But often, they do not provide any argument to justify why such constraints should exist. For example, you can see statements such as we ignore the cross terms, where certain couplings between the various irreducible multiplexes are ignored when constructing the potential. In certain cases, authors do provide certain justifications for constraining the coefficients of the potential. But personally, I do not find many of these arguments very convincing. All these come under the category of an extrinsic constraint, because none of the results can be obtained if you do not impose such constraints on the coefficients. So what I would like to propose in this paper is that we should not use extrinsic constraints. So all constraints that you use in your model should arise intrinsically from the group properties only. Now, this requirement is quite a difficult one, because intrinsic constraints are generally associated with unbroken symmetries. And in Newtonov physics experiments, you don't see a lot of unbroken symmetries. CP is probably broken. Perhaps Newton symmetry is also broken. So the question is, if you do not observe any unbroken symmetry experimentally, is it still possible to obtain constraints intrinsically? The answer is yes. That is what we will discuss in this paper. Now over to part 3, where I will discuss how intrinsic constraints originate in a lot more detail.